Okay, thank you. So we are ready for our first panel discussion, Meet the Department of Energy's National QIS Research Centers. And so I will be turning over this conversation to Jonathan Candelaria, who is the former chair of the QEDC Workforce Development Committee. And I will just remind everybody that you are able to ask questions to this. We appreciate if you could please put all of your questions in the Q&A function. Thank you very much. And John, I will turn it over to you.
Thank you very much, Diana. It's my privilege and pleasure today to host this panel. We're going to hear today from each of the directors or co-directors of the DOE centers, and we'll let them introduce themselves as well as their center. And immediately following their overviews, we'll enter a Q&A where we'll look at the questions that you've submitted, or you can unmute yourself and ask questions. And we're looking forward to a great panel today. So to start with, we'll start with the center that is hosting us today. So Andrew, if you would like to begin.
Thank you. I'm Andrew Hauk. I'm the director of the Co-Design Center for Quantum Advantage, headquartered at Brookhaven National Lab. Our center is really aiming to achieve quantum advantage, to build the pieces that we need to solve useful problems on networked quantum computers in the near future. We have 24 different institutions in our center, 18 academic institutions, 5 national labs, and an anchor company, IBM, one of the world leaders in quantum computing. We have 88 principal investigators and tons of students and postdocs, an ever-growing number with plenty of open opportunities. In our center, we have really some of the real superstars of quantum information science, from the inventors of the ubiquitous transmon qubit that's used in almost all commercial supernetting processor, to Peter Shor, who obviously came up with Shor's algorithm for factoring numbers. Our center is composed of 3 different thrusts in materials, devices, and software, each achieving the aim for a 10-fold gain in that particular domain. In materials, we're trying to understand the link between fundamental properties of materials and microscopic defects and quantum coherence that limits the utility of quantum computers. For this, we're really leveraging the absolutely world-class facilities at Brookhaven National Lab, including the National Synchrotron Light Source and the Center for Functional Nanomaterials. In the devices thrust, we're looking at actually moving beyond the transmon. What kinds of qubits are there that can provide intrinsic protection against noise? Can we find ways to do more efficient error correction in hardware? Can we build transduction systems that can convert between the frequencies used by quantum computers and the optical photons that we need to network those computers? In the software thrust, we're focused on algorithms and computer science. Are there new approaches to error correction and error mitigation that can make what quantum computers we have more useful? Are there algorithms that can really attract problems, especially problems of interest to the Department of Energy with quantum computers? How do we benchmark and compare these ever-growing systems? All of these kinds of questions are what we're answering in the software thrust. Finally, we have what we call the Excite team. It's a cross-cutting team that works with all 3 thrusts to make sure that the advances we find in each area are compatible and to look for things that might fit otherwise fall between the cracks, to make sure that we're truly pursuing this vision of co-design and developing not just individual areas, but in fact, the entire basis for quantum information science. Thank you.
Thank you very much, Andrew. And next, we'll move on to David Ausschlamm.
Thank you, Jonathan. Hello, everybody. My name is David Ausschlamm. I'm the director of QNext, the Center at Argonne National Laboratory. And our mission at QNext is really developing the science and the technology to store and distribute quantum information. So in a way, our goal is trying to take on one of the big challenges in quantum science. How do you manipulate and interconnect entangled states of matter? So we're trying to advance the science and technology in both communication, sensing, materials, and simulation. So to this end, our institutions are building 2 quantum foundries, one at Argonne National Lab, the other at SLAC, that will act like a type of quantum factory, providing a supply chain of high-quality, standardized materials and devices for quantum applications. So in terms of our scientific thrust, we're imaging qubit structures and characterizing their behavior under different conditions with extreme precision. I mean, down to billionth of a millimeter and a millionth of a second. learning how qubits' atomic scale properties influence their performance. We're also developing open source simulation tools that model quantum materials and systems. We're using quantum computers and traditional supercomputers to study the behavior of these quantum materials, algorithms, and devices that operate using multiple qubits. So we're fabricating these systems using really interesting novel material systems in semiconductors and superconductors for qubit production and integrating them into quantum devices with industry. So we're trying to develop the technology also to build optical fiber networks that'll transmit signals in the form of entangled states. And our goal is to connect distant nodes with repeater-enabled links. So really fascinating scientific and technical issue. And to this end, we're looking at quantum sensors, pushing the limits to unprecedented sensitivity. These include sensors that pick up electromagnetic signals with one photon at a time, measure them with accuracy even below the single photon limit through quantum squeezing and entanglement. And like you heard from Andrew, we're supporting about 100 researchers in this program, roughly 2/3 graduate students, and 1/3 postdocs. We have about 100 faculty and staff scientists from 24 institutions across different national labs, universities, and what's a little different here, 12 US technology companies are integrated into the management and research end of the center. And our partner organizations all have opportunities for all of you to engage in this research, to be working embeddedly side by side with any of the scientists in industry or the national labs or universities. So actually, because of our really close ties across these different institutions, our students are really trained at the intersection of industry and academia. So we integrate industry members from all different levels of the organization. And to that end, those of you who find this interesting are provided with a pretty unique window into the quantum ecosystem that is very hard to get solely from the academic side. So a lot of these companies are at today's career fair. It's General Atomics, IBM, Keysight, Zurich Instruments. I encourage you to check them out. Another thing I wanted to mention this morning is that QNext is involved in a pretty exciting initiative driven largely by the students in these centers called the Open Quantum Initiative. It's led by QNext and the Chicago Quantum Exchange, and it's a group of researchers, educators, and different leaders in industry that are championing the values of diversity, equity, and inclusion in quantum science. We feel this is a different way to build an education program with the birth of a new technology. So later today, and actually tomorrow, this initiative is hosting a workshop, which you can also find online, to help all of us develop a program for undergraduate scientists very early in their careers to gain research experiences and build professional networks. We're trying to discuss what are the issues and barriers in this field of quantum technology, as well as really unique opportunities for change in the roles our institutions can play. You know, it's a topic that Sharon just mentioned in her introduction. And the initiative provides fellowships for underrepresented, racially minoritized quantum scientists. Now, I know I'm pretty much at the end of my time here, and I think like all of the centers, we offer seminars for students that are open for all of you to listen to, everything from the fundamental science to commercialization of QAS technologies, and both traditional and non-traditional career paths. So please feel free to check these out on our website, q-next.org, look at opportunities, or contact any of us after this gathering. Thank you.
Thank you very much, David. So next, we'll move on to Anna.
Hi, I'm Anna Grassellino. I'm a senior scientist at Fermi National Accelerator Laboratory, and I'm the director of the new Superconducting Quantum Materials and Systems Center. First of all, thank you to the C2QA management for inviting us to talk about our new center for this wonderful initiative today. And thanks to the Department of Energy for the support of this very exciting initiative, which is the 5 National Quantum Information Science Research Centers. So SQMS, very much like you heard from the previous 2 speakers, brings together the world of national labs, academia, and industry. And that's, of course, one of the very exciting parts, the diversity of backgrounds of the people that are part of our centers. And of course, brings together experts that are in various areas, which are very different, but they are key for the advancement of quantum information science. So, like you heard from Jere and Suzut earlier today, one of the important parts of the quantum centers is to attack a major cross-cutting challenge in quantum information science. In the case of SQMS, we chose something that has been close and dear to our hearts at Fermilab, but in many of our partners' institutions as well, which is the coherence of superconducting quantum devices. So we want to advance coherence of superconducting 2D, so transmon qubits, but also 3D devices, which look like this. And this is what we have been doing at Fermilab for many years for particle accelerators. But now we convert these objects as 3D, very high quality, high coherence resonators for quantum. So this is the mission of our center, is to understand, to go to the very root of what are the limiting mechanisms that cause decoherence. And so what's very key and front and center for SQMS is really the material science, the superconducting characterization, going to really investigate the nanostructure of transmon qubits or these 3D devices and connect the nanostructure interfaces, materials to the actual origin of decoherence. So that there is a very large thrust that focuses on that. So let me step back a second. We have 20 partner institutions. Fermilab is the leader, but I want to mention at least the core partners, which is number one industry partner, which is really embedded in our collaboration, is Rigetti Computing. They're wonderful and very well-known California-based startup, about 150 people. So it's not so small, it's actually pretty large, that builds from scratch, from all the way full stack, from building superconducting qubits to actually building quantum processors and deploying quantum processors. So we work hand in hand with Rigetti, and we hear from the horse mouth what are the limitations today for superconducting quantum processors, and how can we overcome this limitation to reach quantum advantage. We have Northwestern University as primary university partner, and we have also Ames National Lab with their incredible material science expertise, and NASA Ames with the Quantum and Artificial Intelligence Lab from the computational science standpoint. We have a lot of other partners, NIST, and also many other universities, including an international partner in Italy, which is the INFN, which is the Institute of Nuclear Physics in Italy. So our mission, as I said, is advancing coherence. And just to mention a few exciting things that we do, we go from the very fundamental research in materials and superconductors all the way to build better superconducting devices, all the way to then integrate them and scale up into an actual quantum processor. And one of the exciting things, for example, that we're doing in the cryogenics arena is to build a very large record size dilution refrigerator, which will be more than 2 meters in diameter, that will reach a few millikelvin. So we try to attack the problems that are right now limiting superconducting quantum architectures from the standpoint of both coherence, but also system size. And of course, on the application end of the spectrum, being that we are Fermilab and we have a lot of high energy physics partners, we want to employ these systems for very complex problems in high energy physics, but we also have a very large collaboration of condensed matter physicists and also industry in a vast variety of applications, from Lockheed Martin to Goldman Sachs and others, looking at what can the systems that we develop do that is new and impactful. So I think my time is probably almost up. I just want to say that we, like Jeren said, address the problem of quantum workforce from the standpoint of both demand and supply. We spent a lot of time this year hiring a lot of people. We hired more than 70 new people across the center, and specifically at Fermilab, actually more than 40 people. We're very excited about this, and we're going to have a wave of new hiring in a couple of years from now. And we also have launched a lot of training programs like internships, fellowships. So I guess we'll have more time to talk about this, but if you're interested, please come and ask.
Thank you very much, Anna. Next, we'll go to David Dean.
Hello, I'm David Dean, and I am the director of the Quantum Science Center, led by Oak Ridge National Laboratory. And this center is focusing not really on superconducting qubits. We're focusing more on topological qubits and quantum materials. It's very interesting. All of us have the goal of really enhancing the time for quantum information to actually be stored and manipulated. We're trying to work toward the coherence of that information being longer than it is today. And in these topological qubit scenarios, you take a 2D material, say it's a 2D superconducting thin film, or you take something like a spin liquid, quantum spin liquid, and in that material, you can set up things called anyons. Anyons happen to be quasi-particles, combinations of electrons or electrons and holes in the material. And those quasi-particles are actually shown theoretically to protect quantum information when they're manipulated. And that's the key word, theoretically, because these things have not yet been seen experimentally. So a big goal of ours is to understand the anionic behavior in a 2D material, whether it's a topological superconducting type material, or spin liquid material, or even van der Waals type materials in graphene, and in order to, in graphene layers. And when we do that, we're really going to address the fragility of these quantum states through the design and the synthesis and characterization of those kinds of materials. The laboratory system, including Oak Ridge, has some beautiful hardware machines that can actually look at these materials in detail. Here at Oak Ridge, the machines are neutron type, neutron scattering systems. At the other labs, a lot of different types of synchrotrons and photon-based systems, which can characterize the materials that we're interested in. So one of our thrusts is a materials science thrust. Another one of our thrusts is a computational science thrust, which really goes toward fault tolerance algorithms, algorithms that can be used on today's systems, the noisy intermediate scale systems, and also systems that may be a little bit far out in the future. And that algorithm development is coupled with applications in both nuclear and high energy physics and materials science for looking at these algorithms and how they can be developed, quantum algorithms for the materials. So that sets up a nice co-design loop between the two activities. The third activity is in sensing. And in quantum sensing, what we're doing there is designing sensors that could look at milli-electron volts excitations within the quantum materials, because that's what you're going to need to be able to manipulate actually the anyons in those materials. And we're also developing this milli-electron volt sensors for dark matter detection. It's really a nice synergy of science where you have the same kind of excitation energy in both light dark matter, high energy, what we would traditionally call high energy physics, and also in the work toward the materials. So the three of these thrusts work together in an integrated fashion through co-design, which is a buzzword for making sure that everybody works together in a circle. Development of theory, development of algorithms, development of the actual materials, and then back toward the sensors and over again toward perfection. We have 40 postdocs. We have 12 to 15 graduate students funded through the center today. Those numbers are about where there will be for the rest of the term. We are also engaged with 16 partners, 15 partners, including Oak Ridge. 9 universities are in our midst, along with 3 industrial partners. Microsoft is one of our biggest partners there. Cold Quantum and IBM are the other 2, and 4 national laboratories, including Oak Ridge. And it's a great effort, and we're excited about our students and our postdocs. You'll hear a number of things that we do together, a number of activities that they have together, which are very similar to the other centers in terms of journals, workshops, and really focused on the development of the students and the postdocs that are coming through the pipeline. And I'm looking forward to the Q&A, and I think I'll stop right there.
Okay, thank you very much, David. Before we get to our last center, I just want to remind everyone, if you have any questions, please use the Q&A box to enter your questions there. And the directors will either answer them in that Q&A box, or we'll get to them in a few minutes in our open Q&A. So please use the Q&A box. So for our next center, we'll hear from Irfan.
Okay, good morning, everyone. Thank you, John, for the introduction. And again, thank you, Andrew, Diana, and everyone else at C2QA for putting this together and giving me the opportunity to speak this morning. I am Irfan Siddiqui, so I am by training a condensed matter physicist, one that sort of focuses on quantum measurement and superconducting circuits. I am based in Berkeley, California, and there are two labs that lead our center, the Quantum Systems Accelerator. One is Lawrence Berkeley National Lab on equal footing with Sandia National Labs. And in total, by the numbers, we have, again, 15 institutions like the other centers, scores of postdocs, scientists, and graduate students, undergraduates, that we are all excited about convening. In terms of a focus, I think what's important to note, at least from a computational point of view, and the focus of our center indeed is quantum computation, is that a lot of the excitement in the field really started with killer applications, if you like, that would require very complicated, fault-tolerant, error-corrected qubits. And this road is a very interesting and fruitful one that we all wish to pursue in different ways. Our center asks the question, if you look at hardware which is imperfect or noisy, so to speak, what are applications that could be suited for that hardware? And in particular, could those applications, algorithms, and scientific endeavors lead us to a more robust path to fault-tolerant computing? So in a nutshell, that's sort of the focus of the center and how we're looking at this problem from the bottom up, if you like, or NISC forward approach. Looking at that particular question, one then begs to ask the question, what platform to pursue? And so we have not picked one, we've picked several. And the idea is if we pick a few different technological platforms that are at a level of maturity that you can put together quantum systems of some reasonable scale, say tens of qubits, then what could you do with that? And in particular, there are three platforms that we're pursuing, starting from, if you like, insulated or closed quantum systems, or very well protected naturally occurring quantum systems such as Rydberg atoms or neutral atoms, moving on to ions that have stronger coupling, but nonetheless very high coherence times, and then turning that lever to superconducting circuits that are more engineerable, of course, albeit with the challenge of maintaining coherence. So it gives you a sense of the scientific sort of landscape that we're pursuing. And I wanted to make it start off, before telling you about the specific thrusts and details of the center, with sort of a comment on this particular genre of quantum research. And I think it's tremendously exciting, and I'm very thankful to the DOE for being such a strong partner in this sort of change of the quantum revolution, if you like, or this sort of new era of quantum mechanics, where the theory has gone from something very esoteric, known to some mathematicians that specialize in Jacobi elliptic functions, etc., for solving all sorts of things, to something which becomes very, very broad and technologically relevant. And that's tremendously interesting, I think, and exciting for folks that are thinking about a career in this field. That being said, so how does one enter the field? How does one figure out where to pursue a particular direction in quantum mechanics or quantum technologies? My own viewpoint in this is that there is really this tremendous synergy between fundamental science and technology at the moment. So in terms of the fundamental quantum science, there is really an emergent physics or emergent science that really comes forward when you put quantum coherent objects together. And that's tremendously exciting. And of course, the material science folks appreciated that for a long time with quantum materials. When you assemble these sort of naturally occurring systems to exhibit emergent quantum phenomena, we add a knob to that. And that also sort of changes this landscape. If you actually add a knob to controllable quantum systems, then there's a whole other set of physics that's both relevant and exciting. And then there's also technology. And in this primordial soup of quantum systems that have knobs will come out mature technologies. And that's really this primordial soup that we're attacking broadly in this center. So that being said, the structure of the center, the foci, are really revolving around, let's say, four fundamental challenges that we see with near-term quantum computation. Number one, quantum systems are imperfect and have limited coherence. So we don't have sort of the infinite long-lived qubit. The controls for these quantum systems are at the moment not extensible. Many of them are based on commercial solutions. Of course, there are things that are developing in the field, but if you wanted to actually assemble, let's say 100,000, 1 million qubits and control them, that's a very, very hard problem, right, today. Moreover, the domain of meaningful applications for systems that are noisy is something that really needs to be explored. We have very good bona fide proven quantum advantage for things that require very perfect qubits. And finally, what are the protocols to actually know that you have something quantum, and how do you actually apply those protocols to noisy quantum systems? That's yet another challenge beyond simply the growth of quantum, the quantum Hilbert space. How do you actually prove a noisy quantum system is quantum enough to do something? So if you take these 4 challenges, you get basically the 3 thrusts of the center, which focus on algorithms applications, programmable quantum systems, and integrated quantum engineering. So to rattle off a few of the scientific things that we're doing, and then to end the short talk, we are looking at systems level material optimization. So one can make a qubit live very long in isolation. It's an interesting question. How do you do that when you have many such qubits and add wires to them? Right? That's an interesting problem in and of itself. How does one use noise-resilient encodings? Are there more efficient ways to hide your quantum information? And can you do that dynamically? Can you hide it and unhide it on demand when you wish to process it? How do you integrate controls both in the optical and microwave in a way that's seamless, modular, cost-effective for controlling large numbers of quantum systems? And that in and of itself is an engineering discipline of itself. Are there platform-aware simulation, emulation, optimization algorithms that one can run? So if you know that your platform has a certain type of noise or is particularly suited to a certain type of coherence, can you design an algorithm around that rather than trying to do the opposite? This is basically the experimentalist saying that let's have the theorists work a little bit harder, figuring out the right algorithm rather than us trying to design perfect hardware. Beyond that, how do you trade off between robustness and complexity? You can make a very simple qubit, then all the perfection is in the environment. You can make an impossibly difficult qubit and work in any environment. So where is the sort of the balance between these things for a practical technology? Moreover, how do you have scalable benchmarks? And how do you compare, for example, one of the advantages of having different platforms, you can compare the same algorithm on different physical hardware, right? And give you a different insight onto the world around us. So these are sort of the major topics that we're looking at as a center. And again, I think it's very exciting for folks that are thinking about a career at this time, because you can really move the slider from pure mathematics, computer science, to engineering, to systems level engineering, to device level engineering, to material science. So I hope that you share with us this excitement about entering this field, and we look forward to your questions. So I'll stop there. Thank you.
Thank you very much, Irfan. That actually at the end there was an excellent segue, I think, into our Q&A. I think both from some of the questions that have come into that Q&A box, which again I remind our audience today to enter your questions there, and also check out the answers that have been provided already by our panelists. And today I think we're talking about the workforce in general and career opportunities in the centers and in quantum industry and academia in general. So as Irfan was saying, I think it is important to remember that this is a very multidisciplinary field, perhaps one of the most multidisciplinary ones, and there are opportunities for all kinds of backgrounds. One of the questions I want to go ahead and ask any of the panelists to chime in on is to kind of follow up on what Irfan was talking about there. And many times I think people think that in this field, if they don't know all about it, is that maybe it's just for quantum physicists or scientists and maybe even just engineers who have a deep quantum mechanics background, for example, to engage with. So can any of you comment on the range of other skills that are needed now and maybe will be even needed more so in the coming years?
I'm happy to chime in to get things going, Jonathan. I mean, I think as Irfan said, to me, one of the really exciting things about this field is that it's not a physics field. It's a field with physics, electrical engineering, material science, experiment and theory, computer science, all mixed together to really form a new type of discipline. So its progress really relies on collaboration. So I would encourage the students listening in here to jump in, because you absolutely will be able to contribute. And we certainly need all the help we can get.
Maybe I'll just chime in too. There look to be like about 150 people on this phone call. So it seems to me like 150 people, maybe half of them would like to have a job in the future. And what we're finding is that students come with universities, so they're a little bit easier to place. postdocs, all the way across the board, as David said, from material science all the way across to electrical engineering, are a little bit harder to find. And so I think there are major opportunities both within the centers and also generally speaking in this field. It's a growing field, as Sharon said. Huge amounts of funding continuing to come in an increasing way means that the federal government is behind this, and so you will see increases in the ability to find people or to have positions for people that would like to have them.
And I would just add that yes, we do definitely need people who are, have a deep knowledge of quantum mechanics in order to drive these quantum devices. But we also just need people who are quantum aware enough that they can apply their specific disciplinary expertise, whether it's computer science, software, mechanical engineering, right? That, the construction of a quantum computer or a quantum device is going to bring together all of the traditional disciplines. And so we need students who are trained in all of these disciplines to pursue careers in quantum and to bring what they have to the table. Because as much as I hate to admit it, quantum physicists don't actually know everything.
Thank you, Andrew. So speaking of that, again, this range, I think that's clearly going to be important in the future, even more so perhaps. But along those lines, do you see a place currently in any of your centers for students to get hands-on training who haven't already had a PhD? In other words, they're not postdocs. Maybe they're not pursuing a PhD yet. Maybe they're just at the bachelor's level or pursuing a master's degree. Do you see opportunities for those students coming up to get some hands-on training in any of your centers?
I can answer if you want. Absolutely. That's strongly what we believe in and what we're trying to do, for example, with SQMS. This summer, we launched our first SQMS internship, which was even at college level. And also we have some other programs at Fermilab, which are high school level, and we actually tap into those as well. And what we try to do is really training through research, and we have dedicated blocks of time on our dilution refrigerators to really have that sort of like hands-on training. Okay, to really learn what is a qubit, how do I control a qubit, all the different aspects. What is Rabi oscillation? Can I just measure this or that? So we actually, as SQMS, have purchased a dilution refrigerator, which will be solely dedicated to actually training of undergrad, or even, as I said, even earlier than that. And this is also, we're looking at training of technicians, of engineers, and we don't want it to be an afterthought. That's why we don't want to, let's see if there is some time available in some dilution fridge to do this. We decided to just dedicate a test bed exclusively to that.
I could add that one of the wonderful things about having this suite of DOE centers across the country is that they're the stewards of these amazing facilities for research. And this is an extraordinary opportunity for the students, Jonathan, that you just mentioned, to walk into any of the centers, right, and directly engage in hands-on research with these phenomenal facilities, whether they're synchrotrons or free electron lasers, dilution refrigerators, synthesis facilities for materials. There's no shortage of them. And to help get people going, all of the centers have worked together this fall to have a users workshop, which is will all be online, that anybody can tune in, see what these facilities are, see what the research opportunities are, actually get video tours of them, and have ways to participate. So it's a great question. I think the timing is perfect.
And all of the labs have really vigorous internship programs. If you're an undergraduate, you can apply for internships at these labs and participate in the center activities. Most of the companies involved have internships. At Princeton, we have a joint internship program with IBM where you'll spend half your summer learning the academic side and working in the academic side of quantum computing, and half your time working on the industry side. And it's not just gaining experience. I mean, we have a couple of really amazing undergraduates working on our team in my lab that have really pushed our understanding of how materials relate to quantum coherence. They've really driven the project and contributed absolutely amazing work. So our undergraduates are not just getting experience, but they're really driving the research.
Great, thank you very much.
Maybe I can also chime in just for a quick second.
Yeah, you're fine.
Yeah, so I certainly echo all the points that have been made, and the answer is resoundingly yes. There are various places that folks that can plug in, whether they're on a PhD track or a master's track, or just want to actually go on some engineering exploration of the quantum space. One of the things that we are also working on is how to sort of complete the circle and cycle, right? Where we have sort of some input that brings you into the university national lab system for training, for experience, and then also has a particular output for you, whether that's in the industrial domain or with other partners. So we are working with local and state boards in both California and New Mexico and other places to actually go ahead and grease the wheels for internship programs that bring students from that, or folks that are interested in that particular discipline from those areas into the landscape, and then also partnering with our industry partners to see if that there's some way that we can actually hook up these folks to actually look at a long-term career in this way. And again, defining those career pathways and the skills required for them is something we're working on at the moment.
Great, thank you. We had a lot of questions that have come in. Many of them are technical questions. Some of them are application questions. So to all of our panelists, please feel free to pick any one that you would like and answer those online if you can. A couple of questions, I think, or maybe more than a couple here, are related to how transferable some of the skill sets are. So all of you have touched on the many different types of technologies that are being pursued right now, both for quantum computing and, of course, quantum sensing, quantum communications. The basic foundation technology is different, and right now we're exploring all of these to see which ones, as Irfan was saying too, might be the ones that we want to focus on in the future. But how transferable are the skills if someone is focused in one particular area, say ion trap technology or superconducting qubits or something? How transferable are those skills on a hardware level to any of the other technology platforms?
I can take that. The skills are entirely transferable, especially the skills you learn early on. You're really learning how to be a good scientist. When I hire people, I want people with a diversity of experiences because they bring new perspectives on problems instead of knowing what everybody in the field already knows. And so what you learn when you get your first experience is how to do good science, how to set up problems, the language of quantum computing and the types of things that might matter, and all of that transfers to any platform. So you're never at any point locked into some particular physical system.
And I would say that Andrew's got it exactly right. I mean, at the end of the day, no matter what platform you're probing, you're creating, controlling, and connecting quantum states of matter. And all of these share common techniques, whether it's microwave control, photonic creation, electrical readout, right, error correction, devising algorithms that will work in different platforms. The science and technology that underlies all of these is platform independent by and large. So yeah, I think they're completely transferable, which is one of the really nice things about this field.
Yeah, and in fact, as we develop the field, we actually have to have different types of technology moving forward because it's early. It's early in the investigation of these capabilities. And the algorithm building, I'm a theorist, so I get to do algorithm building. The algorithm building actually may work better on one platform than another. So from a theoretical point of view, you might find that having a diversity of capability is good. And the control systems actually tie everything together in terms of the experimental aspects.
And even if it means somewhat of a learning curve, transferring from one to another, it still will actually be very important for the field of QIS. So because it means really importing a certain type of knowledge into another type of architecture, which only can add value.
So again, to add yet a fifth voice, sort of resounding that, I think the proof actually for many of us is that we've had students and postdocs both enter and leave our discipline. So I've had many a postdoc that have come in from AMO or solid state physics and fall in love with superconducting circuits, and folks that are in superconducting circuits go on to the ion trapping or atomic physics domain. So certainly there is portability there. And perhaps one thing to note that many of us started working in fields that were not quantum information science because that field didn't exist at that time. So clearly we have come from various different backgrounds that are somewhat adjacent, if you like, looking backward.
Thanks all of you. Related to that, I guess, extending beyond just the students that are in academia, obviously there are a large number and a growing number of people that are already in industry in various fields who are interested in quantum, have heard about it, curious about it, and so forth. Can any of you give examples of how your centers have provided some outreach opportunities, educational opportunities to people in industry to come up the learning curve and get involved in the quantum space in some way?
Yeah, Jonathan, maybe I'll also quickly start that. I think I mentioned that one pretty unique thing in our center is the really heavily integration of industry throughout the whole center. And with a breadth of 12 industrial partners, it means that we hear from all of them and from organizations you're involved with, like the Quantum Economic Development Consortia. One of their vital interests is workforce development and acquiring talent, and bringing the experience of students and their research projects into their company. So every one of them expressed interest in co-mentoring students, supporting internships. And so to me, this is the best of both worlds. The students in this area get broader experience and networking opportunities, and our industry partners get exposure to our students and our science. So unlike almost any field I've worked in, and as Irfan pointed out, a lot of us in the quantum science area came into quantum information in slightly different pathways. This is a really powerful opportunity. And the reason I think it's going to work well is the excitement of industry in doing this.
Great.
For SQMS, we are launching in a couple of months what we call the pilot program. So we set aside some kind of micro grants that will actually be available for example, industry to apply for some time, for example, in our foundries or test beds. And we have done some outreach, and we will do more outreach, for example, via the Chicago Quantum Exchange, via the QEDC, to advertise these opportunities to build further bridges with industry, beyond the industry, like David is saying, that is already embedded in our centers.
Following up on what Anna said, we also sort of convened our industry partners. So we have an ongoing industry roundtable in the QSA. And in these meetings, we wanted to sort of figure out what are the problems of most import to our industrial partners, rather than imposing those problems from a physicist's point of view, saying that if you were to pick the 10 challenges that your company wishes to address, what would they be and how can we help? And that's been actually very productive, so that we can pair up both industrial partners and scientists at various levels of their career within the center to tackle very specific projects that may be short-term or longer-term, but that goes ahead and nucleates this interaction very specifically and very well-targeted projects.
Thank you. Yes, I think it's clear that again, this is an ecosystem that is being developed here with academic and industrial partners. So they're all welcome. They're all needed. I think is clear. In addition to the industry partners that you have, I know that some of you also have engaged in various programs to teach courses or to have courses. I know Irfan, one of your famous courses that's been online for some years now, to teach the basic principles of quantum computing and so forth. So can you give other examples of how any of your centers or your partners have developed such online type of programs to maybe give students both in academia but also the ones in industry kind of a basic background of quantum computing or quantum sensing, communications, etc.?
At SQMS this summer, we hosted a summer school, and actually the recordings are available for those that are interested. We invited the top level experts in quantum, such as Professor Jens Koch, Annie Paik from IBM, and many more. And it was virtual this year, so it's recorded and available for everybody, and we plan to have more of those in the future, although we do plan to have them in person if the pandemic allows next year. And I do want to mention that they're hosted via our international partner, therefore they will be actually in Italy, possibly next year.
It's interesting that I guess the demand for learning is high. So also last summer, really in May, a little bit before summer. The QSC did its summer school like most of us have now. And we had 400 attendees, not registered, 400 real people actually watching. And IBM was there, so the same people that Anna had. And Microsoft was there doing Q#, and there were workshops in the afternoon that were devoted toward how do I program Hello World effectively on a quantum computer, or how do I do something very simple like diagonalize a small matrix on a quantum computer. And I think those activities really, really help the underlying student and postdoctoral people involved get a hold of what a quantum computer can do, and also on the flip side, what in the world it cannot do. And that's very important too, because the student's going to come in and think it can do everything. You remember garbage in and garbage out from the HPC days. But what it teaches a student is, hey, there's an opportunity space here to actually improve on what's there today. And I think that's a very important aspect of the various types of workshops and summer schools that we're all running. I think eventually, maybe next year, we'll run one all together as 5 centers. I don't know if that'll happen or how that'll happen exactly from Italy, but maybe it will happen. And it will be an interesting avenue for people to really understand where we are, for students to really understand where we are and where we could go in the future. That's the inspirational aspect of what we're trying to do, I believe.
C2QA also ran a summer school last summer. If you're interested, we'll run it again. But I also wanted to point out something that's ongoing right now is every Thursday, C2QA puts out a Quantum Thursday talk, where we invite experts in the field of quantum science and engineering to come and give a talk really geared at early undergraduate level. So we're presenting what are the modern research topics and questions that we have, but to a very, very, very general scientific audience. And so those are available if you want to come and see what's going on with our Quantum Thursdays.
And one other comment to add here, one of the things that we're trying to do in the QSA is to figure out how does one collect all this information, because there's so many things happening at the moment. What are the resources? And I think one of the things the pandemic has taught us that there are certain things that are well done on Zoom. In fact, you may want to do them on Zoom for putting things together. There are certain things that can be done on video playback, right? Certain types of information can be conferred that way. John, you talked about a certain course. Berkeley is certainly recording almost all of its courses at the moment, even though we have in-person meetings, but we're not there yet. And moreover, then there are finally things that you really need an internship. You need to go turn a knob, right, to get a certain set of skills. So we have put together a portal called the One Stop Quantum Shop. And what's happening in this portal as it comes up, it's linking the various activities of these centers, of other partner institutions, NSF centers, et cetera, also linking and using modern networking tools or social media tools that have been sort of reapplied to the quantum domain to pair up folks from the information that's out there, whether it be recorded, interactive, schools, events, et cetera. And we hope that that may be actually a good way for folks that are interested in this field to go ahead and sort of plug into to various things. And there's a C2QA website, as Diana says, all of us have various tools that one can plug into. But I think even making good use of all the information that's out there is a very big step forward, because there's lots of folks doing things in this domain.
Great, thank you. I think we're starting to wind down, so I'm going to give one last opportunity for any of the directors to give us some final thoughts and words of encouragement, whatever they would like to our attendees today. So would anyone like to give just a quick final thought?
I guess it couldn't be any more exciting times to be in the field of quantum information science. And my recommendation and encouragement is to become an expert in something very, very unique that could be, you know, your thing that you bring to the table.
And I might add, this is not a time to be shy. So if you're interested, I would say immediately reach out to any of these centers, right, through the information on their various websites. And there's no reason not to get engaged now, you know, whether at the undergraduate, graduate level, postdoc level, you know, high school level, there are lots of opportunities in all of these centers. So I would encourage you to do it early.
You get a chance to play with deep, strange, weird, fundamental science, and at the same time, do something that actually is useful and practical and could shape technology for the next several decades. It's great. Come join us.
Great. I think just one last question, actually, that I thought of that's come up here a little bit in the Q&A, and apologize, we couldn't get to all of the questions. There were a ton of good questions here. There was some questions about remote versus on-site now. I know everybody probably is in slightly different stages of reopening, but are there opportunities now for people to come back to campus yet, or is it still a little bit more remote, I guess, in some of these internships that you mentioned and opportunities with your centers?
For us, John, classes under 200 people can meet in person. Classes above 200 people are virtual. In terms of internships, labs are allowed at 100% density, so people can come in and out. However, the travel restrictions from various countries, et cetera, do have to be respected in quarantine periods, et cetera, as we do this.
Okay. Any of the other centers? How are you starting to accept new on-site interns in your programs?
We certainly are at the University of Chicago, and most of our participating university institutions and the laboratories are opening up as well. So I think there are lots of opportunities to do this on site now, with the usual travel restrictions that Irfan mentioned.
Okay, great. Well, I want to thank all of you for a great session. I know we could have gone on for hours here. Again, there were so many great questions that came in. Please check them out if you have a chance to type in some answers. And again, I want to thank all of the panelists today. Tremendous opportunities out there for you in the audience. Please take advantage of them. Reach out to each of the center websites. And with that, I think I will turn it back over to Diana.